Hi students, welcome to B.Tech. In this video, I am going to explain you the concept of stability in S domain, particularly about Routh-Hurwitz stability criteria. So let us move into the topic. First we see the definition of stability. What is meant by stability? A system is considered to be unstable if it does not return to its initial position. So first we see what is meant by initial position. You take the pendulum in a wall clock. So what happens? You take a pendulum in the wall clock. If you touch the pendulum, then the pendulum will oscillate between 2 points. After some time, the pendulum will come to its original position. So if it does that, if the pendulum does not come to its original position, then we can say that the system is in a state of instability. But if it comes to a state of rest, then we can say that the system is stable. So this is what the example for stability. Okay. Now we see the conditions for stability. A system is said to be stable if it produces a bounded output for a given bounded input. That means if you give a bounded input to the system, it has to produce a bounded output. Then, if there is no input given to the system, then the output must tend to 0 irrespective of the initial conditions. That means what might be the initial conditions of the system? The system output must reach to 0 if it is subjected to a 0 input. So these are the two conditions that are to be met by a system to become a stable. But it is not always possible to have a system to be stable. Now let us see what are the types of stability. We talk about the stability in terms of its relativeness and absoluteness. So a stability of a system may be referred in two types. One is absolute stability, another one is relative stability. So the term relative stability is used in context with or in comparison with some other system. That means suppose you take a simple example for the concept of this relative stability. We have some people in our family. So for example, age. You take age of a person as an example. This age is absolute one. You take your age as an example. So age is an absolute quantity. Okay. Suppose if you compare your age with somebody else, your brother, so then you may be younger, elder or young. So younger or elder is called relativeness or comparativeness, and your age itself is absoluteness. Like that, the stability may be an absolute stability or a relative stability. Okay. So you might have a doubt how this stability is related to this mathematical models that we have formulated so far. Here in the time response analysis, we find out or we determine the response for a given set of inputs. Okay. So the response characteristic as t is tending to infinity, the system may settle down at one particular value. That means by looking at the transfer function of the system, it is possible for us to assess the stability of the system. Okay. So here first we see what are meant by poles and what are meant by zeros. Before going into that, I am considering a single input and single output system as an example. Here, the transfer function of a single input and single output system can be written as G of S is equal to the ratio of C of S by R of S, where C of S is the output parameter and R of S is the input parameter. It is nothing but the Laplace transform of output C of S and Laplace transform of input is R of S. And in general form, it can be written as C of S by R of S is equal to B naught S power m plus B1 S power m minus 1 plus O1 plus Bm. This is the numerator divided by A naught S power n plus A1 S power n minus 1 plus A2 S power n minus 2 plus so on an. Here this m value is always less than n. Okay. So Here, the denominator polynomial of the transfer function is known as characteristic equation. That means you take this denominator polynomial and you equate that to 0. You will get an equation. That equation is known as characteristic equation because this characteristic equation is having highest power of s equal to n. So that this characteristic equation will have n different values for the s. What are the values? That is this secondary thing. Okay, so here I have taken the denominator and I equated this denominator to 0, and that equation is a naught s power n plus a1 s power n minus 1 plus so on plus an is equal to 0, where a naught value is always greater than 0. So if you solve this equation, you are going to get different values for s. Those values of s are known as poles of the system. Depending upon the values that are we obtained for these s, the stability of the system is determined. So now we see the condition for stability. We can express the condition for stability by observing the location of the poles of the closed loop system. Here you might have a doubt. What is meant by a closed loop system? Is nothing but in the block diagram reduction technique, we identified or we find out the equivalent transfer function of a big system, and that big system is written into a single or simple equation form, so that that equation contains some denominator in it. If you equate that denominator to 0, that itself will become the closed loop system. So the nature of the response is decided by the roots of this characteristic equation. To have a system to be stable, that means to have a bounded response or to have a bounded output, then the roots or the poles of the system should have negative real parts. Then only the system will have the bounded response for a bounded input. So that means you equated the denominator polynomial to 0 and you find out the roots of the characteristic equation. You got some values for the s. In the test, you check whether you have a negative real values for the s or not. If all the s what you got have negative real parts, then blindly you can say that the system is stable. If not, the system is not stable. So this is the thumb rule what you need to remember while answering the questions for stability. Okay. So to understand the concept what I told just now, let us see this with the help of a first order system. Here, a first order system is a system whose order of s is equal to 1. So that in the general equation, you substitute n is equal to 1. If I substitute n is equal to 1, then I will get an equation a naught s plus a1 is equal to 0. This equation is a first order characteristic equation. Here, you solve this equation to find out the value of s. So if you simplify this, you will get that value of s as s1 is equal to minus a1 by a naught. You know that this a naught is greater than 0, so that a naught is always positive. Then if this a1 is positive, then I can say that s1 will be a negative value. If not, if a1 is negative value, then I will get my s1 as a positive value. So depending upon this s1 value, we can say that the system may be stable or unstable. So in simple words, I can say that the system is stable provided if both a0 and a1 are positive. It's simple. If A0 is positive and A1 is positive, then we are going to get S1 as a negative value so that the roots will have a negative real part. So, to have a system to be stable, the coefficients of S must be positive. That is what we have seen for the first order system. Okay, now we see how would be the coefficients for a second order system in the next video. Thank you.